Okay, so this is the start of the revision videos about P2, which is radiation and life. And now the radiation that they're talking about here is usually, or most for all of it, electromagnetic radiation and how we use that in everyday life and how it affects us. Now electromagnetic radiation, we're going to come on to in a second exactly what it is. But the first thing we need to know is what radiation itself is. So radiation is just a flow of energy from a source, okay? So radiation is just when energy moves continually from a source. Now, it's not always dangerous. It can be, but it isn't always. It's important to remember that if someone says radiation, don't immediately think you're going to get cancer. Some of them can do that, and we'll go into that then later on in a different video. But a source, then, is just something that emits radiation, okay? So the radiation flows out of it, and usually we draw it in a kind of wave, and we'll see why later on as well. Now, there's three things that can happen when this radiation, so I'm going to label that radiation, hits something, hits an object, and depending on what the radiation is, and depending on what the object is, one of three things will happen. It can either be transmitted. Now, transmit means to travel straight through. So this radiation goes straight through. Now, an example of that we all know about is light and glass. I'm going to write light, glass. Glass transmits light. It goes straight through. It's transparent, we say. The second thing that can happen is that it can be absorbed, and that's kind of drawn here already. Now, absorb means it can't get through. So for light, and to go back to the same example, for light, we could say that could be some black card. Okay, so black card would absorb light. It stops it in its tracks. So the final thing that can happen is it can be reflected. Now, that means the radiation hits there, and then it comes back, and it bounces off. So it bounces back. That's what reflection is, okay? Now that happens for light, as we all know, I'm sure, in a mirror, okay? Light, it happens for a mirror. However, for different types of radiation, this will happen for different things. So, for example, gamma radiation is transmitted by black card, and it's transmitted through most mirrors. Infrared radiation can get through your clothes, some of them, but it wouldn't be able to get through, say, a white t-shirt. It's more likely to get through a black t-shirt than it is a white t-shirt because it's reflected from a white t-shirt. Actually, it's absorbed by a black t-shirt, so that's not completely right. But some other colours it will go through. So different types of radiation transmit, absorb and reflect different things. So now we know what that is, we need to think more about electromagnetic radiation itself, and it's all part of the electromagnetic spectrum. Now, a spectrum is just a continual continual family of something, and here it's a continual family of waves, and we can see here that we've said it's a family of 7 electromagnetic waves, okay? They've all got different frequencies and wavelengths, but they travel at the same speed. Now, we say they're a family because they've got related properties, so we've said they all travel at the same speed. They can all travel, one important thing to do, they can all travel through a vacuum. They're all made of basically the same thing, photons, which we'll go into in a second, but they're all to do with the fluxation of electric and magnetic fields, so the movement of electromagnetic fields. So that's why they're all called a family, because they're all made of basically the same things. The things that make them different and that make their properties different is the fact that they've got different frequencies and different wavelengths. Now, if you remember, the wavelength of a wave is the distance from one peak to the next. So that's one wavelength, and I have that called lambda, so wavelength. So here, these ones have got a longer wavelength than the waves down here. Now that means that these correspond to radio waves, we'll go into this for a second, and down here it'll be gamma waves. They've got the shortest wavelength. So this way, lambda is decreasing. Now if we remember back to P1, we talked about the wave equation. The wave equation was simply that the speed of a wave, v, is equal to the frequency of a wave, f, times the wavelength, lambda. Now, frequency is how many waves pass a point per second. So you can imagine if these waves all travel at the same speed, which they do, and that speed is the speed of light, which is 300 million kilometres per second, 300 million metres per second, 300 million metres per second. If they all travel at the same speed, then the shorter the wavelength, more of these full waves are going to pass each second. So that means the frequency increases, okay? So if I decrease the wavelength and I keep the speed the same, I have to increase the frequency. So if I draw an arrow that way, this way it should be f decreasing. So radio waves have got the highest wavelength, but got the shortest frequency, the lowest frequency, whereas gamma waves have got the shortest wavelength and the highest frequency. And that's really important later on when we come to energy. Now let's look at the other waves in the family. So this is the electromagnetic spectrum. Lots of information here. The 7 those that we need to know about are 1, radio waves. And this is in order from longest to smallest wavelength. Radio waves, microwaves, infrared, visible light, ultraviolet radiation, X-rays and gamma rays. So it's really important that you know that order. Okay, there's people who've got different mnemonics they use. I think one that was on a clip that we watched in class was read my instructions visible under X-ray glasses. It's not the world's best mnemonic, but you know, if it helps you, it helps you. Now, there's all different diagrams here and lots of information. So, the first thing here, penetrates the Earth atmosphere. We just got a yes or no. So, radio waves do, visible light does, microwaves and infrared don't, ultraviolet, X-rays, gamma rays generally don't, but some of them, sometimes as an exception. We'll see that later on. This here is a nice picture of our wavelengths. So we can see again that radio waves have got the longest wavelength and that gamma waves have got the shortest wavelength. And from that we know that the frequency is the other way around. So gamma is the shortest, the highest frequency even, and radio waves are the lowest frequency. Here, to help us kind of think about the sizes of these, because this isn't how big they actually are, the waves. They're much different to that, and they're invisible, so we can't really see them except for visible light. There's some comparisons of sizes. So the wavelength of a radio is about the size of a building or even bigger. So they can be up to kilometres long, radio waves, okay? So that's why it says 10 to the 3, that's a kilometre, okay? The one complete wave, so one full wave, can be over a kilometre long. Now when we get into microwaves, we're getting to the stage kind of between humans and a honeybee. So a honeybee here is about 10 to minus 2, that means centimetres. So if I write kilometres there, this is getting to centimetres, okay? So about the size of a bee is how long a microwave is. We're getting a lot smaller now. Infrared is 10 to the minus 5. So that's like 0.01 of a millimetre. So we've written here a pinpoint. So the size of the head of the pinpoint, that's how big infrared radiation is. So really, if you could see that, you wouldn't be able to see the difference. You wouldn't be able to see the wavelengths so much. Visible light is smaller again. It's half of 10 to the minus 6. Now we call it a micrometre. Okay, 10 to the minus 6 is micrometres. Protozoans is a type of organism. It's biology. I don't know too much about it, but they're really, really small. When we get to ultraviolet, we've got even smaller again. We're getting to nearly tens of nanometres here, sorry. So this is tens of nanometres, which will be useful to know for your chemistry exam, because you have to know things about nanometres for that. And that's about the size of a molecule, so the width of a molecule is about a nanometre. When we get to X-rays, 10 to the minus 10, so we're now 0.1 of a nanometre, or hundreds of picometres, okay? This is the size of an atom, so we're getting to really, really small lengths. So if I had an atom here, the wavelength of one wave would be about the same for an X-ray. And finally, gamma rays, 10 to the minus 12, this is picometres, called PM. And they're about the same size, or smaller than all the time, of atomic nuclei. They're the tiniest things, okay? They can be smaller than this as well. So they kind of carry on that way. Like radio waves carrying this way, you can have radio waves that are 100 kilometres across. You can have gamma rays that are much, much smaller than this, but we class them all as gamma rays. Now down here we've got the frequency, and you can't see because it's not in colour, but you can see here that the frequencies 10 to the 4 down here and 10 to the 20 here, which means our frequency is increasing that way. Like we said before, it's decreasing as we go towards radio, increasing towards gamma rays. And finally, there's something about temperature, but we're going to look at that later on. So that's a quick intro to the EM spectrum. But I said before that they were all made of a certain type of thing, and that is a photon, okay? So all of the waves in the EM spectrum are made of photons. Now, a photon is a wave packet. It's a small section of an EM wave that can act as a particle or a wave. And you may have heard of quantum mechanics, and that's what this is all based on, the fact that some things can act as particles or waves. Now, we don't really need to go into that too much. That's just something that we need to know about. So if I think about my original EM wave, I'm going to draw one like this. All I need to do to think about photons is that I split it up into small little packets, like this. Okay, so actually I get, these are my photons, that kind of thing. Now often we draw them with an arrow at the end to show that it's a photon. It's just small little sections of wave. Now, a gamma wave is going to have a higher frequency and a shorter wavelength than a radio wave. So I might have, say for a radio wave, it might look like this, radio. Whereas for gamma, it might look like this, because we can see there that it's got a shorter wavelength and a higher frequency. Now, the energy of a photon depends on the frequency. And it's kind of hard to see this, and I've not drawn it later on, so I might need to go back to this here. Maybe I'll go back to here. So, the higher the frequency means you've got a higher energy. Equals higher energy. So that means that if frequency is decreasing this way, this also means energy is decreasing this way. So gamma rays are the most energetic. You can't even read this, can you? Energetic. And radio waves are the least energetic. But as long as you remember that gamma waves are the most energetic, that's a really easy way to remember what you need to know. So, this is really important for intensity, okay? Intensity is something different. It's the amount of energy that arrives at a square metre of a surface every second. Okay, so imagine this here is 1 metre square on a wall, maybe. Now, I think of it in terms of light. Another word for intensity is brightness. So when we think about light, if you've got a more intense light, it means it's more bright. So if I think about a normal light, every second I might have, 4, 5, this is obviously more than a second, 8 photons hitting it. That's obviously a gross exaggeration, you'd have a lot more than that. I've just lost where my corner is, there we go. Have a lot more than that. But let's say we've got 8 photons a second. Now, to increase that energy, this is visible light. Okay, to increase that energy, I could do 2 things. I could either, 1, have more photons hitting the surface every second. So I'm still going to have visible light, which is my orange pen, but there's more of them each second, so it's going to have more energy. Now, if you think about this, we tried it in class with a scrunched up ball of paper, and we threw it against a wall. Now, to get more energy against that wall, you could just throw more paper balls at it. So more photons every second is going to be more energy, therefore it'll be more intense. The other way is to hit the surface harder. Okay, so if you were throwing paper balls at a surface, if you hit the wall with more force, you'd be adding more energy to the wall. The way we do this with photons is we can't throw them harder because we don't throw them. We throw an energy that has more energy. I throw a photon that has more energy at the wall. And we've just talked about that. The photons that have got more energy are these. They're gamma rays. Okay? So maybe if I throw a gamma ray, but at the same speed as my original, so still got 8, but now they've got more energy for each of them. More energy will have reached that wall, will have arrived at that square metre of surface. So the intensity will be increased that way as well. That's quite difficult to understand, but that's the way I like to think about it. Now, the final thing we need to know about is how EM waves travel. Okay, now it travels in straight lines usually, unless it's reflected off something, but we can draw that in different ways. So there's 3 different types of diagrams. Now, the first is a ray diagram, and we draw that. I've got a light bulb here because it's just easier for this kind of thing to just imagine light, because we're used to light a lot more than the other ones. So a ray diagram, EM radiation comes out in straight lines, and the arrow shows me what direction the radiation is going. So I can draw as many as I want. There we go. Straight lines, these are rays. The next way I can do it is in waves. Now waves, I draw them as a kind of wave crest. So it looks a bit like, you'll see, ripples on a pond. Okay, so imagine that my light bulb is where I've thrown a pedal in a pond. And for that, I'd get this kind of ripple effect. So these are the waves radiating out. The final way that I can draw them is with photons. And this is going to take me a lot longer. So I do lots and lots of little photons coming out. And you can see how the arrow is going in the direction that they would travel. But because there's so many photons, they're so small, like you need literally millions to be able to see something if it's visible light. It's going to take me far too long to draw them. But you can get the idea. So I can draw these photons, and then I can see that individual particles coming out of that light bulb. Now, intensity, we said, remember, was how much energy arrives at a square metre of surface every second. If you think about it, the further away you get from a light, the less intense it looks. And that's because the less energy is reaching your eye. If you look here, if I had a line here, if I was stood at this point, I'd have a lot more rays, they'd be closer together, hitting the wall, than if it was here, because here, they're further away. So that means it's more intense. The light has spread out. Same with the waves, same with the photons. So EM radiation spreads out as it travels. Very important to know that. And that means that the intensity decreases the further away you are from the source. And that makes sense. I always just remember it by thinking about a light. If I'm stood near a torch, it's really bright. If I'm stood a mile away, I'll barely be able to see it if it was pitch black. Although, admittedly, the human eye can see a light from over 7 miles away, I think, in pitch black. So, you'd still be able to see it, but it'd be a lot dimmer because it's a lot more intense. So that's an intro to the kind of general ideas about EM induction. Not EM induction, EM radiation. The next one I'm going to go on to is ionising radiation and how that can damage us. Okay, hope that was helpful.